In our last video, we introduced the concept of rates of change by approximating slope from both tables and graphs. We're going to get a little more specific with rates of change. In fact, there are two types of rates of change. Our learning target uses some acronyms, so let's take a look. It says define the IROC as the limit of AROC. The I stands for instantaneous and the A stands for average, and don't worry, we'll spell that all out in our notes today. But we're going to learn how those two rates of change are both different and related to each other. I wanted to start these notes with a really big idea about this course, and that is that calculus is the mathematical study of change. So that's why we've started talking about rates of change, and yes, it does mean slope, and I think that surprises a lot of people that basically calculus, the first half anyway, is based upon something that you learned about back in Algebra 1. So we're just going to build upon that knowledge that you already have about slope. The first type of rate of change that we're going to talk about is the average rate of change. And we'll keep referring to this graph up here, this picture, to help us visually distinguish between average rate of change and the second type, which is instantaneous. So average rate of change is the change between 2 points. And when you connect those 2 points, it gives us what we call the secant line. So the average rate of change is the slope of the secant line, and again, it joins 2 points. The good news is the formula for the slope of the secant line, or the average rate of change, is what we've already been practicing in our previous video. It's just the formula for slope between 2 points. So when you are approximating slope from that table or graph, you are actually finding the slope of the secant line, so joining those 2 points. And again, that expression is called a difference quotient because it has differences in both the numerator and denominator. You might agree that this difference quotient that we started using in our last video is a little bit cumbersome as far as all the subscripts and the notation is involved. I often say this looks kind of like physics because I know in physics you guys use a lot of subscripts. So us calculus students and teachers, we like to use more simplified and streamlined notation. So I hope you'll appreciate that we're actually going to improve that notation. Instead of using the x2 and x1, we're going to use a and b to represent those x values. So this is the formula I'd like you to memorize as the average rate of change formula. And let's see if we can apply it to our first example, which asks for the average rate of change of this function f of x on the interval -4 to 5. Since that's a domain, those are x values, and we're going to use a and b to represent those in our formula. What I've done so far is just say that the average rate of change is equal to, this is the formula. I copied it once just because we're learning it, and as soon as you feel comfortable, you can jump right into substituting the a and b values into that formula. So it would be f of 5 minus f of -4 over 5 minus -4. At this point in the calculation, you have a choice, and this is totally a preference thing, up to you. You can make this a really long divisor line and evaluate both your f of 5 and f of -4 on that line, and that's totally fine, but some people get a little overwhelmed by all of those operations in the same place. So what I chose to do instead, and you might like this option, is to just do a little side work. I figured out my f of -4 and f of 5 values, and now I'm going to transfer those values back over to my difference quotient. From my side work, and it's a little cut off here, I got 40 for f of 5 minus 4 for f of -4, so that's my numerator, over 9. Notice that double negative did turn to a positive, and then I simplified, reduced, so my final answer is 4, which means the average rate of change of this parabola, if you were to look at the points at -4 and 5 and connect those 2 points with a line, as we see in our graphic here, that slope would be +4. Okay, I'm pretty proud of myself because I figured out how to fold the paper over so that we could see both the graph still and this section on instantaneous rate of change. So let's talk about what that means graphically that's different from our average rate of change. So your instantaneous rate of change at one point is the slope of what we call the tangent line. And again, that touches one point of that function only. I mentioned earlier that the instantaneous rate of change and average rate of change are different but related, and here's how. You'll notice that we have our formula for average rate of change here, the f of b minus f of a over b minus a, but in front of it we have put a limit as b approaches a. So what we're trying to do is get those two x values in our average rate of change formula to converge into one x value. So what you can do, and it might be difficult to visualize, but I want you to try seeing that the point at A and the point at B, if they were to start moving towards each other, they would converge upon one point that happens at this C value. So even though we might be able to visualize that happening, mathematically it's not true that two different x values are really going to approach each other. So mathematicians figured out that it made more sense to have the limit as x is approaching that one in particular value C. So they rewrote the expression for instantaneous rate of change, still with that format of the average rate of change, but very important to know that there's always a limit statement attached to that. So it's the limit as x goes to C of f of x minus f of c over x minus c. So let's try using that formula for this first time in this example. We're finding the instantaneous rate of change of the function x squared plus 3x at x equals 2. That 2 is the value of c that you're going to see substituted into our formula. So let's get started. So all I've done so far is what we just talked about, and that is to substitute 2 for all the c's in our formula. And then moving forward, I've got to figure out what it is that I need to write to represent f of x and f of 2. Well, luckily, f of x, we don't have to overthink that. That is just going to be our function, x squared plus 3x, written right here, followed by minus our function value at 2. So let's try that. So I've copied down my f of x just like it appears in the problem, followed by my minus from the formula. And then you have a choice here again, much like we saw in the average rate of change. You can evaluate f of 2 right here in the quotient, or you can go off to the side like I did, and my side work keeps getting cut off. Double check me, but 2 squared plus 3 times 2 I believe is 10. So I decided just to insert that value there. In our denominator, there's no simplification needed yet, so we've just got x minus 2. Notice, very important, I am carrying my limit statement every time I make a simplification. So let's go from there. I'm sure you guessed that this numerator can be factored, and if you've really been paying attention to our limits this year, you probably noticed that most of the time something will cancel out. So I did get this x minus 2 factor and an x plus 5, and in my next step I'll cancel that and evaluate the limit. After canceling the x minus 2 factors, I was left with the limit as x approaches 2 of just x plus 5 for my numerator. Substituting the 2 plus 5 gave me a final answer of 7 for the instantaneous rate of change. So what that means is if we were to graph this parabola and look at exactly x equals 2, that tangent point of the tangent line would have a slope of exactly positive 7. There's one last topic about rates of change that I want to address in this lesson, and it's when you have two rates of change that are actually in opposition or opposing each other. And what that means is that you have a positive and a negative rate that are working against each other. This is a topic that comes up in a lot of AP questions, so I'd like to save this example for us to do in class together. See you then.